because they're saying good managers create market inefficiencies to gain profits, like so non-economical.
Okay, so the reason I took some time out to talk about delta functions was so that I could be a little bit more careful about actually writing Gauss's law and when you actually solve for the electric field. So when, for example, we're talking about a line of charge, let's make this line of charge go in the z direction, and I'll put it at the origin in x and y, right? When I'm talking about a line of charge, what I'm really talking about when I write that down is that the charge density is equal to the charge per unit length along the rod, okay? And delta x, delta y, telling you that all of that charge per unit length is at x equals 0, y equals 0, right? That way, when I do the integral over here, x and y just drop out of the integral, right? So it makes life a lot easier on the volume side of this equation to write a line like that. If I have a sheet of charge, then it would be sigma, the area density in, let's say, the xy plane, times delta in x. So that just tells me all the charge is along that line. Having said that, we can now get sloppy about it. And I'm just going to skip writing the x and the y integrals, for example, over here, right? So if I had that charge density over there, then the right-hand side of this equation would be 4 pi times the integral of lambda dz. I just did the other two integrals. Yeah, I like delta functions.
They're fun.
All right? So, but I haven't specified any limits on here or anything of the sort. So now I might ask you to solve for the electric field at some distance r from a line of charge. So you want to find the electric field here. And the first question that you should ask yourself is it easier to integrate all the electric fields over the entire length? And for some of you, you just do that integral in your head and you're fine. All right? I do have a joke, irrelevant joke. It's a von Neumann joke. Tell me if you've heard it. All right? Apparently, and this is supposedly true, there was a party in Chicago that he attended. Have you heard this one? All right? That he attended, and one of his friends came up to him and posed him this problem. You've got a train, and the train is traveling towards Chicago.
Who was it posed to? Newman.
What? It was posed to von Neumann, who is the master of series solutions. The train is traveling at a certain speed, and then what you do is you launch. I think the argument, the thing was that it's a pigeon, and the train is traveling very slowly, and the pigeon flies to Chicago, turns around and comes back. In that time, the train's traveled a little distance, turns around and goes back again, comes back, and so on. How far did the pigeon fly? Right? And the way that all of us who are clever think about this is we say, oh, the pigeon's flying at a certain speed, and the train is traveling at a certain speed. We know how long it takes the train to get from here to there, and from that, then we can solve for the total distance that the pigeon flew, right? Von Neumann answered the question in a second, and his friend said, I thought I could fool you into doing the series. And he said, I did. So for some of you, the integral might be easier. Then fine, you just go ahead and do it at home, right? But for others of us, in particular me, I have to rely upon being a little bit cleverer than that.
Mere mortals.
Mere mortals, right? So what we do is we look at this problem and we ask, before we start doing integrals, is there symmetry to the problem that could make it doable in using Gauss's law? So the first thing that we observe is we look out here at almost n, because this is an infinite line here. We're going to take the infinite. If it's finite, you have to do the integral, tough-o. But you look at this and you ask, is there anything special about the field? And the first thing we conclude is that the field must point out. Because for every point over here, I can find a corresponding point over there, and the two are going to cancel in the z direction. So the field only points out. That's good. Okay? Then the other thing that we could do is we could look at this and we could say, does it make any difference at all which direction we look at the line from?
No.
Right? And it doesn't. It doesn't matter whether we're at distance r on this side or distance r on this side, or if we look at it from the top. If we drew a circle around here, we find out that's the circle. That the field is constant over that surface, and that the field points out everywhere. Okay? So, the field points out, and I just chose a quasi-circular surface here, such that the normal to the field, so that's the field, and the normal to the surface points out as well. Proportionally out. Right? Normal to the surface points out as well. That means that when I do that integral over here, over the circular surface, it's going to be the field times the area of the surface and nothing more. Okay? Then, because the field points straight out, I haven't finished my surface yet. I know that I'd like to have a circle in the plane, right? But what does it look like on the top and on the bottom? Well, the field is pointing out. So it makes life easy if I choose my surface, that I'm going to do my integral over there, which is now called a Gaussian surface. I choose my surface to be perpendicular to the line, because it's parallel then to the field, which means that E dot normal is equal to 0 at the top and at the bottom. So I'm going to choose a Gaussian surface that's supposed to be symmetric. That is, this is actually a good representation of that circle as I have drawn. But it's all supposed to be symmetric. I choose a Gaussian surface, which looks like, I don't know whether you guys use such things anymore. A soup can.
Chef Boyardee.
You probably get your soup in baggies and... But anyway, there used to be a thing that was called a can.
They still sell Chef Boyardee in them.
It's shaped like that. Much like the inside of a toilet paper roll. All right. So, this is the soup can model surface. And then I ask what the integral over the surface is. And the integral is the integral over the top surface, dA top, right? Plus the integral over the bottom surface, plus the integral over the sides. And if this comes out to be simple, then I solve my problem, because the other side is really easy for me to solve, okay, for the electric field. Well, this one is 0, and this one is 0, because the dot product is 0, okay? And this one is the integral over the surface of EDA, because the field is perpendicular to the surface out on the sides over here, right? And because the field is constant over the surface, I can pull it out of the integral. So that's just the side area of my soup can, which I'll take to have height, let's call it h, right? And radius r. So that surface area, power of chalk, is 2 pi r h. That's all. Now what about the integral on the other side? This guy here. That's got to be equal to 4 pi. Integral over the length. Lambda is a constant, so I pull it out. dz, that's h. Right? So h cancels out, and I'm left in CGS units with electric field is equal to lambda over 2 lambda over r. Okay, so Gauss's law gave us a really nice way to solve that problem. There are only about 3 problems that can be solved using Gauss's law. I'm serious. Spherical distributions of charge, constant linear distributions of charge, and surfaces. Actually, a constant distribution of charge over a very large surface, an infinite surface. Okay, that's about it. There are a lot of variants on the problem once you're working in spherical coordinates, right? We can, as you did for your homework problem, have a radial dependence that can be complicated. But it's still radial, and the problem's just the same problem. Okay. What about, oh, I should have left that up there.
How many times have you said that this lecture?
I don't know. Yeah, I think I said it 3 times.
Something like that.
You have it taped.
Yes,
so
I
you
do.
can actually count all the times.
I'm going to.
Okay. So now the next problem that is of general interest is the one where we have a very, very large surface. And in physics, very, very large means infinite. Okay? With a constant charge density on it. So I want to technically write the charge density. It's sigma delta in z. Okay? So that charge is in the xy plane. Right? And my Gauss's law (4 pi charge enclosed). I'm going to make the same set. Well, the first question is, do you do the integral, or do you use Gauss's law? We didn't put this up unless we use Gauss's law for this one. So we're going to use Gauss's law. And the reason is that if I analyze this charge density on the surface, if it's that's a constant charge density, for a charge over here, let's say I'm interested in that point there, I can always find a charge over here, such that the electric field only points out, right? And then by symmetry, I can say that the electric field above the surface must, at a given distance, must be equal to the electric field below the surface at a given distance, right? So I've got symmetry in the problem as well. And then that means that I want to choose some Gaussian surface that's going to take advantage of the symmetry. I'll choose my various surfaces so they're either perpendicular to the field or parallel to the field. And the surface that makes the easiest sense for me to draw here is what we call the soup can surface, okay? Where the top and the bottom are parallel to the surface of interest, and the sides are perpendicular. Since the field points out, the integral on these sides is 0, and I look at the top here, and my field on the top, my integral over the area on the top is E times the area of the top surface, so that's pi r squared. I'll call this r. And I'll call this distance out, because it looks cylindrical. I'll call it z. Okay? So it's actually E of z pi r squared. I don't know what it is yet. But at the exact distance on the bottom, same distance on the bottom, z off the bottom, the field's the same. So my bottom surface is E of z pi r squared. Right? That's the whole flux. through that surface, and the charge that's enclosed is the charge density times pi squared, right? Lots of things cancel out here. 2e pi squared goes out. Yes. The electric field is 2 pi sigma. Independent of distance from the plane, because I took the plane to the infinite. Right? So once again, Gauss's law gives a really quick solution to this problem. Right? Let me see. Done. Yeah. Okay. So there are a couple of ramifications of Gauss's law that I want to mention. And I need to make a statement first, which is that if I have a conductor, a material that is a conductor, in electrostatics, what that means is that if we set up some charge distribution, we wait with the conductor until the charge distribution, like I put charge on something, and then I wait until the charge distribution has equilibrated and charge is no longer flowing around the problem, or around the volume, okay? So you wait until charge has gone somewhere. Well, here's what we know. Oh, and charge flows freely in a semiconductor. It's at a limited speed, but it flows freely in a semiconductor. That's the in a conductor. That's the definition that we're going to use. So that means that if we have a situation where we establish a field in a conductor, that what's going to happen is that there's going to be a consequence. The charge moves as long as it feels a field, and it keeps moving until there's zero field. What that means is that if I had a chunk of conductor, and then I applied an electric field, and initially I'd have that electric field, so I turn it on, and 1 picosecond later, there's the field. It's in there, okay? Then what's going to happen is that the mobile charge in the conductor is going to move so that I put a net negative charge on this side and a net positive charge on this side. And that net positive to negative charge is going to introduce an internal field in the material, which is going to make the sum of the external and the internal field equal to 0. So inside a conductor, the electric field in electrostatics is 0. Later in this course, we're going to get into electrodynamics, where then we have to worry about how quickly the conductor can respond, right? But for now, in electrostatics, the field is 0. The macroscopic field is 0. Locally, it turns out, of course, that the local field is always not 0, because you've got atoms and atomic densities and protons and electrons and all of that. Locally, look at it, it's not 0 at all. But over the scale of microns or greater, actually tenths, hundredths of microns or greater, the electric field is 0. So in a conductor, the electric field is 0. That has a consequence right away. Got from Gauss's law. Rewriting Gauss's law. Oops. Q enclosed, right? And the conductor, the electric field is 0. So now, if I have a conductor, chunk of conductor here, right? If I put net charge onto that conductor, so let's say I put some positive charge onto the conductor, Gauss's law tells us that all of that charge must go to the outside of the conductor, to the surface. Doesn't tell us about the distribution of the charge. Yes.
5 minutes.
Oh, okay. It just tells us that it goes to the outside surface of the conductor. Why is that? Because I can always choose a Gaussian surface just inside the surface of the conductor. And the flux through that surface must be zero because the electric field is zero. So that means that all the charge has got to go to the outside because there's no charge enclosed, right? So that's one quick conclusion. The other, so that's a charge, all charge goes to the outside. A corollary to that is that means that the charge density, the net charge density inside the conductor must be zero. So charge density inside a conductor is zero. Well, that follows from the electric field being zero because I can take divergences as well. But I'll say that that's all a consequence of, once you know the field is zero, then Gauss's law tells you all of this. Resides on the surface, field is zero, net charge density is zero. That's all that we're going to do right now as far as ramifications of Gauss's law, but more will come later. You look like you're about to try to ask a question, Ryan. No? All right. So now for something completely different. But really completely the same.
It's all under Maxwell.
What?
It's all under Maxwell's equations.
Yeah, okay. So, we know, I've said this before, relationship by definition between the electric field and the force that acts on the particle is that, right? Linear relationship. But from mechanics last semester, earlier, you know that the work that you do in taking a charge from one point to another is, and I'm going to screw up the signs here. I promise you. I'll screw up the signs, but I don't care. I'll just grade you on it later. Q, 9, Q, integral, yes, over the path. So, yeah, I'll use S as my variable that I'm going to integrate along with that. So the line integral of the electric field from point A to point B is the work that has to be done. Do work.
Isn't it you that
Goes up. I'm not sure whether I got the sign right, but I don't care. I'll make sure when I write the definition down that I get the sign right. Okay? And I'm going to write the definition in a minute. So we can then say, well, we've got this electric field in space, and I showed you a moment ago that there is some scalar that is when you take the gradient of it that produces the electric field. I look at this and look at the fundamental theorem of calculus here. I think that's the one that I can use. Right? I can take derivatives, and I find out that the change in potential energy between 2 points, A and B, can just be written as this. So I just take the charge out of the problem. That's the change in potential energy, barring a sign error. And this is the thing that I can eliminate the charge and just ask about that property of space, which is the electric field. Right? It's really easy to do this for a point charge. If I had a point charge at some point in space, here, what we typically do but we don't have to, with finite distributions of charge, what we will do is define the potential at infinity be equal to 0. So that's our reference point. potential at infinity being equal to 0. Okay? And I can go ahead and do that integral and figure out what the value is, and I find out then that phi at some distance out, the potential at some distance out, minus the potential at infinity, which I'm going to set to E equal to 0, is for a point charge of charge Q prime, let's say, equal to Q prime over R in CGS. There'd be a 1 over 4 pi epsilon naught in MKS units.